We are Group 15 and we will be presenting our findings and results from our course project. Here is an outline of what we will be covering in the presentation. I will now explain the problem, its evaluation criterion, and our strategy. The dataset comes from the ELO Merchant Category Recommendation. For this problem, we need to create a definite metric for the company to gauge customer loyalty. It is calculated using anonymized features and previous transaction histories of the customers and merchant data. Submissions are evaluated based on the RMSE between predicted and actual loyalty scores. The lower the RMSE, the higher our ranking. Here is a breakdown of our team strategy. It consists of EDA, feature engineering, building machine learning models, post-processing, and evaluation. Moving on to EDA. There is a total of 5 different datasets, and we identified the problem as supervised regression. Missing values and outliers are present in the datasets. In the training set, there are over 200,000 data points and 5 features, of which 3 are anonymous. The features are categorical while the target variable is a float. One finding in the presence of outliers is the target variable despite it following a good distribution. Another finding is the low correlation between the anonymous features. The other 2 datasets are from the historical and new merchant transactions. The historical set contains 3 months of transactions per card ID. It has over 29 million transactions and 14 features. The new merchant set contains 2 months of transactions from new merchants. It has 2 million transactions and the same 14 features. The features are mostly categorical and there are missing values. One finding is the high count of outliers from the installments feature, which had to be dealt with in pre-processing. Also, the purchase amount feature seems to be normalized due to its low variance and negative values. Lastly, the month lag feature helps to differentiate historical from new merchant transactions. Historical lags are negative, while new merchant lags are positive. Moving on to dataset comparisons. Based on card IDs, no duplicated cards were found between the training and test sets. Also, cards in the historical and new merchant sets were identical. However, not all cards from the training and test sets are found in the new merchant set. We then explored the merchant's dataset, which contained merchant category IDs and merchant IDs. Based on the merchant category IDs, not all categories from historical and new merchant sets are found in the merchant's dataset. However, based on merchant IDs, all merchants from historical and new merchant sets are found in the merchant dataset. In summary, there is low dimensionality in all datasets. There are missing values to be inputted, and there are low correlation between features. Supervised regression techniques have to be employed. Thus, we have to manipulate our data and engineer meaningful features for our machine learning models. When handling missing values, it is crucial that we input good estimates. Missing values in historical and new merchant sets were inputted with their modes. Next, outliers were replaced with the median values. The bulk of engineered features came from the aggregations of existing features. They were used for achieving higher prediction accuracy as compared to each constituent learning algorithm alone. Statistical values were used for creating them. Feature interactions were also used to engineer new features. When models use features to make a prediction, it is influenced by the feature interactions as well. These interactions were captured in the form of ratios and differences between some of the 150 plus features. They help to increase our ranking by more than 10%. Lastly, feature transformation was also employed on the historical and new merchant datasets with the purchase date feature. A new set of 80 features were created and we merged the different datasets into a single training set. From feature engineering, we now have a total of 190 features. These features were added progressively after running many models. It was also noted that the encoding of categorical features into integers improved our ranking.
In this section, we will be discussing the machine learning models that were implemented by the team, starting from creating the baseline models for a benchmark, followed by model selection and model hyperparameter tuning. Since our problem was a regression model, we tested our popular regression methods including linear regression, random forest, decision trees, gradient descent regressor, and support vector machines. Although these models helped create a baseline, they provided a highly biased result and hence were not suitable for future processing. Amongst these models, the random forest regressor performed the most promising results and hence was considered as one of the base models for future ensemble learning model construction. Light gradient boosting is an ultra-efficient boosting technique that can be used on large datasets while not compromising on the model accuracy. The previously chosen 130 features from the KS test were used to train our LGBM model. After performing hyperparameter tuning, the shown parameters were chosen for the best performing model. In fact, the standalone LGBM model performed better than some of the more advanced techniques such as some architectures of stacked ensembles. A simple deep learning model structure was chosen to implement and train our regression model. Consisting of several dense layers, we also included dropouts between the layers to reduce the effects of overfitting. This model did perform better than our baseline model, but was unable to outperform the optimized LGBM model. Based on the observations from the various baseline models that were built, we proceeded to conduct hyperparameter tuning using various methods to extract the best performance for our models. Bayesian optimization heavily relies on probability and the Bayes theorem. The optimization technique was applied to the LGBM model and was able to improve the leaderboard position by a massive 10%. Grid search CV techniques were employed to find the best parameters for our random forest regressor. This greedy method is computationally heavy but is able to achieve and identify the best parameters for our models as it searches exhaustively through the search space. K-fold cross-validation was used throughout our training process. Using a folds method for cross-validation helps ensure that the model performs well not only on the train space but also on the test environment. 17 folds were employed to train our best model for submission. Regularization is a technique that helps us reduce the impact of overfitting. Therefore, they can prove to be highly useful in our overfitting problem. L1 and L2 regularizations were implemented but weren't able to produce much difference in the results on our baseline models. Bayesian-rich regularization technique was also employed in our stacked implementation of ensemble learning. Early stopping is a technique that was used while training our deep learning model to ensure that the model does not overfit on the training data. Early stopping helps stop the training early by monitoring the validation loss over a few epochs. If there is no considerable improvement, the early stopping callback is able to stop the training, hence preventing overfitting. In this section, we will be discussing the final model implementations that helped us bag spots in the top 8% and the top 8.56% in the public and private leaderboards.
To climb the leaderboard and improve the model performance further, we used some advanced techniques which included ensemble learning implemented via stacking and blending. The main objective of ensemble learning is to improve model performance in terms of accuracy by aggregating the predictions of multiple models. To implement this, we first constructed a set of base models from the training data and then made predictions by combining the predicted results made by each base model. Here, the chosen machine learning models are LGBM, XGBR, RF, deep learning, and decision tree regressor, which were used as the base regressors for stacking and blending. Blending generalization is used in the final layer. These techniques were applied by the team to improve our performance on the leaderboard with the help of the predictions from the baseline models. The 2,207 data points with target values less than -33 are labeled as outliers. For ensemble learning purposes, light GBM methods were used by us to classify the outlier data points, achieving an AUC score of 90.77%. Bayesian-rich blending is then used in the third layer of blending. It provides a natural mechanism to handle insufficient or poorly distributed data. In our case, due to the presence of outliers, this optimization proved to be useful. And the formula that was achieved in the end was that the final result is equal to the single LGBM model prediction minus the binary outlier prediction times 33.219281. This stacked model provided us with the best position on the public leaderboard in the top 8%. Other versions of the stacked implementations were inferior as compared to the single LGBM model that was constructed and optimized. The stacking model of the heterogeneous regressors, which were of LGBM, XGBR, RF and DL in the first layer, random forest regressor and LGBM in the second layer, followed by Bayesian ridge blending in the final third layer, has not been able to produce a better result than the single LGBM model. Moving on to solution novelty, which highlights the unique techniques and solutions we tried to implement our model and get a solution for the problem that we had at hand. Firstly, we constructed an LGBM with non-outliers, and considering that we had 2,207 data points that were defined as outliers, having a model that would predict without the outliers was one of our novelty points. Next, we then built a classifier to predict those said outliers so that we can separately classify the outlier values that we had found in our data set. Then we also blended our predictions, and we had implemented that with Bayesian ridge, as I had mentioned earlier. And lastly, we used stacking with Bayesian ridge in the final blending process. And the use of novel methodologies such as a classifier for the outliers during predictions, as well as the use of ensemble learning, helped boost our position on the leaderboard by a lot. In this section, we will discuss the feature importance that was extracted using the KS test. The KS test, as previously explained, was essential in improving our performance and also in reducing the number of redundant features in the dataset. This helps not only in an increase in the performance, but also in a reduction in computation time, as there are lesser features to learn from. This slide summarizes the various experiments conducted by the team and the progression of the same over time. After laborious efforts in implementing optimization techniques, feature engineering to create new columns using aggregates, ratios, and feature interactions, the team was able to achieve the position of top 8% and top 8.56% in the public and private leaderboards respectively. In this section, the team will summarize the efforts and also provide our key takeaways and lessons learned through the course of this 13-week-long project. Here is our team. So, these are the key takeaways for Abhinaya. She was able to learn and understand the machine learning pipelines and the importance of feature creation and feature engineering in enhancing performance of a model by leaps and bounds. As for me, I learned the importance of hyperparameter tuning in improving model performance, on the importance of ensemble learning, how to infer data from EDA, feature creation, as well as how to appropriately test model and analyze the results that are obtained. As for Mr. Jitsha, for him, the key takeaways were that he understood the importances of EDA, the importance of having data pre-processing as a process in the machine learning pipeline, feature selections with models optimization, post-processing, as well as ensemble learning. And finally, for Jordan, his key takeaways were feature engineering, hyperparameter tuning, as well as post-processing. With this, we have come to the end of our presentation. Thank you for your time and attention.